Hello, good afternoon. Today we will discuss hypothesis testing and how hypothesis testing hypothesis testing is used in operation and supply chain analytics as a part of business analytics. So hypothesis testing is mainly around drawing inferences about two contrasting propositions relating to value of one or more population parameters. So these population, suppose you say the average height of people in MBA class of 100 students is 5 feet 8 inches. So here you are talking about population parameter, that is height of students. And of course you know that population class size is 100 students. Other population parameter could be the average education of a group of people, or it could be about any demographic information. So these are the population parameters like age, weight, average height, mean weight, or the average education level. So these things, if you say, make a proposition about it. So suppose you want to describe an existing theory, you put it as a null hypothesis, that is at zero. And to every null hypothesis, there is an alternate hypothesis, that is complement of h zero. So if I make a statement, there is always a counter statement. And from we take a sample from the population, because we cannot take data about the whole population because the population could be large in size. So we using sample data, we reject the null hypothesis, and we conclude that from the sample data we say that sufficient evidence to support alternate hypothesis. Or if we fail to reject null hypothesis, then from sample data we does not support H1, that means null hypothesis is true, we fail to reject it. And we, from the sample data, if that inference, we can do inference about that population parameter. So for example, we said that average height is 5 foot 8 inches for that particular class, and we took sample of 10 students from that class, and we made an hypothesis, did a hypothesis testing, and then based on that we can extrapolate it to the whole population. Whatever the hypothesis we have done, whatever statement we have made, and that we accepted, we then extrapolate it to the whole population. But the testing, hypothesis testing, is only done based on the sample data. So what is the procedure for hypothesis testing? So I would say for there are 5 steps. First, we identify the population parameter and formulate the test hypothesis. So we say, what is the population parameter? Is it average height? Is it average weight? It's a average IQ level? Or is it the average nutrition level? So what is the population parameter we are interested in, and we want to make a statement about it and check it. And then we formulate the null hypothesis and the alternate hypothesis. So we make a statement and then alternative statement. Then we select the level of significance. What is the error in drawing the correct conclusion? So normally in social sciences, we take error ranging from 1% to 10%. In general, we are okay to live in social sciences. We take 5% error in drawing an incorrect conclusion is acceptable. But in certain situation, we have to bear with the 1% error. So once we select a level of significance, we determine the rule decision rule on which to base the calculation. Then we come up with a decision rule that whether we're going to use p-value, t-test, and what is the critical value that we are looking at, and what t-level we gonna decide on, and then we collect the data and calculate the test statistics. So next is collection of data from the sample, and we calculate the test statistics around p-value or t-value or confidence level, and then on that particular sample we apply the decision rule on the test statistics data, and then draw a conclusion and say that this hypothesis is true, and based on that, that's why our statement regarding this particular population parameter is true or false. There are three. Then let's normally talk about one or two sample test. So normally, suppose we take only one sample from the population. So our null hypothesis will be this parameter or the from sample the population parameter. It could be, let's say, for example, let's say average IQ level. So mean IQ level of the class of 100 student, MBA student, and then we have a directional thing that it is less than equal to or more than equal to or equal to a particular constant. Let's say IQ level, we say mean IQ level is equal to 110, and alternate hypothesis will be the mean IQ level. Suppose if you take in null hypothesis less than equal to, then here it will be more than, and suppose in the null hypothesis it is more than equal to, then alternate hypothesis it will be less than, and suppose the null hypothesis is equal to constant, then in alternative it will be not equal to constant. So suppose I say null hypothesis is mean IQ less than equal to 110, then it will be mean IQ level more than 110. Suppose it is more than 50, more than equal to 50, then it is less than 50, or equal to 100, then it is not equal to 100. Suppose we take two samples, and then we normally go for difference in mean, and then null hypothesis will be between the two samples the mean IQ level of sample 1 minus equal, suppose we this can come on the this side of the sign also. So say difference of the IQ level, mean IQ level between these two samples is more than equal to or less than equal to or equal to, similar to here, 0. And alternative hypothesis is difference of mean IQ level between these two samples less than, if this is more than equal to, this is less than, if this less than equal to, it is more than, if it's equal to, then it is not equal to. It is not correct to formulate a null hypothesis using more than equal to, less than sorry, more than equal to is correct. It is not correct to formulate a null hypothesis using more than or just less than or not equal to. So correct notation of null hypothesis is always more than equal to or less than equal to or equal to. So these things this is the right formulation of null hypothesis. And normally when we hypothesize something, we always make an error. We make a statement. There's always an error that we are okay to live with. That is a type 1 error. Is called notation is alpha, level of significance. So it is level of significance. The type 1 error alpha is, it occurs when we reject null hypothesis. In fact, when the null hypothesis is true. And value of 1 minus alpha is confidence coefficient. So not if the error is type 1 error is alpha, level of significance, then 1 minus alpha is called confidence coefficient. So equal to P not rejecting H0 when H0 is true. Correct? And the value of alpha can be controlled. Normally we fix value of alpha in advance. Common values I told you in social sciences 1%, 5% or 10%. Normally we will be living with something like this. This is the most common acceptable value. And it is very important to understand what is alpha, level of significance, and because it's going to be used significantly in statistical test as well as when we do hypothesis testing. So if this is type 1 error which is rejecting H0 when H0 is null hypothesis is true, the probability of making type 2 error. Type 2 error called signified shown by beta, which is not rejecting H0. H0 is false. When you're looking to reject it, but you don't reject it. The value of 1 minus beta is called power of the test. Like 1 minus alpha is the confidence and 1 minus beta is the power of the test, which is rejecting null hypothesis when H0 is false. So your probability of rejecting null hypothesis when H0 is false. So you always want power of the test to be high. Right? You want power of the test to be high. You want confidence coefficient to be high. You want type 1 error alpha level of significance to be low. The value of beta cannot be specified in advance and it depends on the value of the unknown population parameter. Okay? So alpha normally you fix in advance is 1%, 5% or 10%. This is 0.01, 0.05 or 0.1. But beta cannot be specified in advance. It depends on the value of the population value parameter that you are trying to find. So let's see, look at all of them. Suppose null hypothesis is then mean IQ level or the population parameter of that you're finding in a particular sample is more than equal to a constant. Suppose this is one sample, the test you are interested in, and then hypothesis one is parameter less than equal to constant. So always look at alternate hypothesis. If this sign in alternate hypothesis here is less than equal to, then rejection region is always, suppose this is the normal distribution curve of the probability. The whole area is 1, area under this curve is 1, and then and this value is level of significance alpha, and rejection region is anything if something lies in this region, right? And this is called lower tail. We always do lower one tail t test in such thing. And suppose null hypothesis parameter from the sample is less than equal to constant and hypothesis 1 alternate hypothesis parameter more than constant. So if the sign is in alternate hypothesis is more than, then it's always here, it's a upper one tail t test, and the rejection region is this shown by alpha, and critical value is this is the critical value. So anything that lies here, value lies in this region, suppose that calls for rejection of null hypothesis. And suppose our null hypothesis is the mean IQ level equal to say 100. So parameter the the measured in the sample from the sample data, population parameter measured from the sample data is equal to constant, then a hypothesis parameter is not equal to constant. In this case, the significance level is divided by 2, made half, and it is lies on the both side of the normal distribution curve. So alpha by 2 is here, alpha by 2 is here, and then we put it that to rejection, the two rejection regions. So it is both lower tailed and upper tailed. So it's called two tailed test. But one thing you note here, where the value of in each upper tail test on the right hand side and the lower tail test on the left hand side is alpha. Here the value, the area under it is alpha by 2 and alpha by 2. So it is just half, but it divided into both side of the normal distribution curve and put it as two tail test. We will look more into it when it will be clear to you when I show you an example. So we want, I told you, we want power of the test to be high. The power, it can be normally power test. Normally we'll go for large samples. So when we use the large sample, it enables to detect small difference between the sample statistics and population parameters with more accuracy. And suppose if you're going for smaller level of significance, low alpha, then we try to compensate by having the large sample size. And the power test is high, then it is allow us to make valid conclusions. That's why we want, if alpha is low, then we want large sample size so that our power of the test is high. Now we are looking for T sample the test statistics. Suppose you are dealing with numerical data. Whatever data collection you have done from samples is numerical in nature. So it is parametric. Parametric means it is scale or it is interval. Then we normally, if there are two groups, then we go for two group unpaired t test. If it is more than two samples, we go for ANOVA or F test. ANOVA is analysis of variance. But if it is some ordinal or nominal data, it is not interval or scale, then we, if it is not interval and scale, if it is ordinal or nominal, then we go for two group Mann-Whitney U test, Wilcox or Wilcoxon rank sum test. If there are more than two groups, so rather than Mann-Whitney U test, we go for Krug-Wallis H test, or some people call it Krug-Wallis ANOVA. Suppose the data is not at all numeric, it's a categorical in nature, ordinal in nature. Then for the non-numerical data, if there are two groups, we go for chi-square test. And if it's more than two groups, again also we go with chi-square test. I'll just show you an example that will clarify the things for you. So either we do the hypothesis testing using the critical value, where the critical value lies in the rejection area or not. Other way is we can do the hypothesis testing using p-value. And if p-value is less than alpha, so earlier in critical value is in the rejection region, two tail test or in one tail test, then it is null hypothesis is rejected. Or in the p test, if p value is less than alpha, then you reject the null hypothesis. And p value is a observed significance level, is a probability of obtaining a test statistics value equal or two more extreme than that is obtained from sample data when the null hypothesis is true. I will give you some example and I'll also tell you how to calculate p-value and the critical values. For lower t-test, the p-value is the probability of the left of the test statistics t in the t distribution, and it is found using Excel function t distribution value of t n minus 1, n is the sample size, and then true. For upper one tail test, the p-value is probability to the right of test statistics test asterisk t, and it is found using Excel function 1 minus t distribution t and minus 1 true. And for two-tailed test, the p-value is found using the Excel function t distribution 2t, and then bracket t is the t test statistics, n is the sample size, minus 1 if t more than equal to 0, more than 0, and t distribution 2t minus t and minus 1 if t less than equal to 0. Let me quickly show you how to do that. If I go to my Excel sheet, in Excel, if I can show you here, and you want to calculate, you know, critical value is normally found by T inverse of 1 minus alpha. So I can always go here and I say T inverse. It's a function in Microsoft Excel. You can choose it. You ask for probability that I give you. We always look for 1 minus alpha critical value. 1 minus 5% is 95%, 0.95. Degree of freedom is n minus 1. Let's say, let's go up here. And, and if you want to do two distribution, just I told you, p-value, if you would find, you can always look for, suppose a two-tailed test. So you go t distribution 2t, and you can get 2 minus 69, put the value of degree of freedom. Okay. So this gives you an example how using both t distribution values can be easily found out using Microsoft Excel. So we go back to and give you some more examples. Let's look at one example which will clarify the things. Suppose you say that in a particular call center and people are calling, and the response time that within 24 seconds somebody will pick up the phone. So people call, some people come and call center makes a claim that within 24 seconds somebody will pick up the phone call if you call them, and confidence level is 95%. So alpha level of significance, they are looking at error, type 1 error is 5%. Sample, we did a sample, so to justify, to test this null hypothesis, we did a sample, we took a sample of 44 calls. So degree of freedom is n minus 143. T value that we figure out, T is calculated. I will show you how to calculate T value. T is calculated as minus 1.05. So critical value for this case is, you can always say this is because here you can see it is less than 24. So it is definitely left tail test, and critical value figure out it T inverse for the T1 minus alpha n minus 1. So T inverse 0.9543. Using Excel, I just showed you the value we found 1.68. So critical value for this is 1.68, and this is the alpha region here, and this is the critical value. So area, this is the rejection area. And what is the calculated T statistics we found out for it? T calculated is minus 1.05, which is here. So it is not in the rejection region. So we cannot reject. Sample mean, I'll show you, came out to be 21.91. From sample, it is looking at our response time is less than 24 seconds. But we found out we cannot use, when we did this hypothesis testing, we figured out we cannot reject the claim that call center mean response time is more than 24. So that means that of course it is less than 24, and we okay, so this is one we failed to reject at 0, that our response time is more than 24. So we have to do some recalibration in the call center process flow and make sure that again take the sample and again do the hypothesis testing till we are convinced and we can show the test result to our customer to show that our call center response time is in fact less than 24. Let's take one more example here. What is happening is there's a milk bottling plant and they are filling up milk in a bottles, and their sample mean is coming as 1.05, and people are claiming and that saying that they are filling up less than 1 liter. So they took sample, and from the sample they did a hypothesis testing. Let me show you this example in Microsoft Excel. So you confidence how I came up with this value, you can easily come up with this value is you just type here equal to confidence. It will ask you for alpha in this case is 0.55%. It will ask for standard deviation in our sample is 0.15, and it will ask you for the sample size, which is 200. Here you can see we took 200 bottle sample. It come out to be 0.021. So of course average milk per bottle supposed to be 1 liter, and we reduce this value from our 1 liter, that it becomes 0.979, and then add it to this thing. So our confidence interval goes from 0.979 to 1.021. And of course we are looking at one tail test, that our mean amount of milk in a bottle is more than 1 liter. So for this this become the rejection region. So we did a sample mean 1.05. You can see 1.05 is somewhere here, so it doesn't lie in the rejection region. Yeah, and that means our null hypothesis is true. We cannot reject the null hypothesis that that the average amount of milk in one bottle is more than equal to 1 liter. So this is using Microsoft Excel. One can easily do the hypothesis testing. Some more example I'll show you. Let's go back to our Microsoft Excel and let's say two-tailed hypothesis test. So if we go to a company and they say average age of employees is 35 years. So our null hypothesis is mean age equal to 35, and alternate hypothesis is mean age not equal to 35. So we took sample of 35, so n minus 1. Oh sorry, average age. Number of sample size is 34. Sample mean of these 34 people, sample mean the age is coming out to be 38.67. Samples and standard deviation is 7.85. So how to calculate t? So I just showing you that how to calculate t, and t statistics, t is calculated by x mean minus mu 0 standard deviation divided by square root of the sample size. So we can easily, the sample mean is coming out to be 38.677, and we are looking at population mean, which is mu 0. This is something that we are hypothesizing or making a statement about, that we want there in the population the average of employees 35. So you can say 38.6 sample mean minus population mean. This is standard deviation of the sample divided by square root of sample size. So t statistics coming 2.73. So critical value is t distribution, t inverse 2t alpha and n minus 1. We can easily find out from the Microsoft Excel that I showed you here. This is the value we found, t inverse 1 minus alpha and minus 1, 1.68. Let's see what we are interested in. Oh, we are t inverse 2t. So I want to equal to t inverse 2t. It will ask you a probability 0.05, degree of freedom, that is 43. Oh, it's 33. 2.03. So let's come back to our, yeah, here 2.03. Now let's look at p-value. P-value we get from t distribution 2t. This is p distribution 2t. This is the value we are interested in. How do I get it? Let's say t distribution 2t. It will ask you as mean 2.69, 2.69, and then degree of freedom 33. It's 0.01. So p value is less than alpha. P value is less than alpha. What is alpha? Is 0.05. So we reject H0. Other way, if you want to look it from so this example show you all the possibilities. First is p values we calculated, and it is less than 0.05. We reject H0. Other way is we look at the critical value 2.03, and what is t? 2.73. Yeah, so critical value is 2.03, and t is here. It lies in the rejection region. So using both the example, we show that we have to reject H0, that mean age of the employee in a company is 35. So it is not equal to 35. Yeah. So it is also something that was little bit indicator was given from sample mean, but we cannot infer anything just based on sample, we have to do proper hypothesis testing. Let's look at, suppose they are here, we talk about two samples. Once this is one sample, this is one sample, this is also one sample, and I gave you some example about two sample. When you talk about two samples, you can do the null hypothesis like we talk about mean age of one sample from one and the other sample, their mean age is difference is equal to 0. This is something you can make a null hypothesis. And mean age of two sample, their difference is not equal to 0. That could be alternative hypothesis. So this is two sample. But suppose if, what if we have more than two samples? Suppose we have three samples. One example is there are three machines which are doing this milk filling, and we are noting down their time to fill up one bottle. So we took six samples and machine 1, 2 and 3, and we found out the mean time to fill up the bottle. Correct? And we found out the mean of the mean. So if you have more than three samples and you're making an hypothesis that mean of this is equal to mean of this mean, and this three means they are same, they are not different. Suppose you are making this hypothesis about means of more than two samples, for example. So let me go back and show you this thing in Microsoft Excel. Suppose you have three samples and you want to do their hypothesis testing, and you can usually do it using, I told you more than two samples, you have to do ANOVA test. And we go to data analysis. And people who don't know how to get this data analysis icon here, you can go to field and you can do options, and within the add-in in Microsoft Excel, you have analysis tool pack option available. You select it and click OK. You come to data analysis, and then here we go for, so what we have to do is ANOVA single factor. And how we do it here is you scroll down, there must be ANOVA here. Yeah, ANOVA single factor is come up. We input the range, we input the whole range, group by column, label in the first row, alpha is 5%, and then we click OK. And because output option is new worksheet, so you see the new worksheet option has come up. F critical is 3.68. This is the first thing we look at, and F value is 6.95. So F critical and F is more than F critical. So we reject the null hypothesis that mean filling time of all three machines are same. So three samples we are doing here, hypothesis testing. So we reject the null hypothesis that all the mean filling time of three machines are, there's a significant difference among the three machines. So what is the alternate hypothesis? There's a significant difference among the three machines filling time. Okay, so this is how we do the hypothesis testing when we make statement about some population parameters, and using the sample statistics we prove or disapprove the null hypothesis or the statement, and then make an estimate about the population parameter, about the parameter that is of interest for us to discuss, share and use in decision making. Thank you very much. I hope you like this presentation. I look forward to keep talking to you.